Welcome to the session on interpolation with unequal intervals. All the interpolation formula we discussed in the previous sessions hold good only when the values of the argument, that is the independent variable x, are equally spaced. If the values of x are given at unequal intervals, the definition of differences for equal intervals is not applicable. In such situations, we make use of a new kind of differences called divided differences, which take into consideration not only the changes in the values of f of x, but also those in the values of x. In this session, we shall make use of Newton's divided difference interpolation formula. Let f of x naught, f of x1, etc., f of xn be the n values of a function y equal to f of x corresponding to the arguments x equal to x naught, x1, etc., xn, which are not necessarily equally spaced, where that is x1 minus x naught, x2 minus x1, etc., xn minus xn minus 1 are not necessarily equal. The first order divided difference of f of x corresponding to the arguments x naught and x1 is defined as f of x1 minus f of x naught divided by x1 minus x naught. It is defined as, it is denoted as f of x naught comma x1 or divided delta f of x naught. Here we use x1, or another notation is x naught comma x1 like this. These three are the notation of first order divided difference corresponding to the arguments x naught and x1. Similarly, f of x1 x2, that is the first order divided difference corresponding to the arguments x1 and x2, is denoted by f of x1 x2, which is defined as f of x2 minus f of x1 divided by x2 minus x1. We can use the notation like this, divided delta f of x1. Here we use x2, and like this x1 x2. This is another notation. Similarly, f of x2 comma x3, that is the first order divided difference corresponding to the arguments x2 and x3 is equal to f of x3 minus f of x2 divided by x3 minus x2. We can use this notation, divided delta f of x2. Here we use x3, or x2 comma x3. Similarly, we can define all the first order divided differences. In general, we define the first order divided difference corresponding to the arguments x r minus 1 and x r as f of x r minus 1 x r is equal to f of x r minus f of x r minus 1 divided by x r minus x r minus 1. We can use the notation as divided delta f of x r minus 1, we write here x r, or we can use this also, this notation, x r minus 1 x r. The second order divided difference of f of x for 3 arguments x naught, x 1, x 2, corresponding to 3 arguments, we can define the second order divided difference as, the notation is f of x naught, x 1, x 2, which is defined as f of x 1, x 2, that is the first order divided difference corresponding to the arguments x 1 and x 2, minus f of x naught comma x 1, which is the first order divided difference corresponding to the arguments x naught and x 1, all divided by x 2 minus x naught. This is the second order divided difference corresponding to these 3 arguments x naught, x 1 and x 2. We can use this notation also, divided delta square f of x naught. Here we write x 1 comma x 2. This is the notation. Thus, we require 3 continuous arguments for the second order divided difference. The third order divided difference corresponding to 4 arguments x naught, x 1, x 2 and x 3 is defined as f of x naught, x 1, x 2 and x 3 is equal to f of x 1, x 2, x 3, that is the second order divided difference corresponding to the 3 arguments x 1, x 2 and x 3, minus f of x naught, x 1, x 2. This is the second order divided difference corresponding to these 3 arguments, that is x naught, x 1 and x 2, all divided by x 3 minus x naught. We can use the notation like this, divided delta cube f of x naught. We write here x 1, x 2 and x 3. This is the third order divided difference. In order to define this third order divided difference, we have to use 4 continuous arguments, that is x naught, x 1, x 2 and x 3. In general, the nth order divided difference corresponding to the arguments n plus 1 arguments x naught, x 1, x 2 etc. x n is f of x naught, x 1 etc. x n is equal to f of x 1, x 2, x 3 etc. x n minus f of x naught, x 1, x 2 etc. x n minus 1 divided by x n minus x naught. Here f of x 1, x 2 etc. x n is the n minus 1th order divided difference corresponding to n arguments x 1, x 2 etc. x n. This is the n minus 1th order divided difference corresponding to n arguments x naught, x 1 etc. x n minus 1. This can we have to use this notation also, divided delta raised to n f of x naught. Here we write x1, x2 etc. up to xn, x1, x2 etc. up to xn. This is the notation. The divided differences of various orders can be displaced in a divided difference table as the values of argument, the values of arguments are x0, x1, x2, x3, x4, that is the 4 arguments, and the corresponding function values are f of x0, f of x1, f of x2, f of x3 and f of x4 are given. Then the first divided difference, divided delta f of x, that is f of x0 comma x1. First next difference is f of x1 comma x2, that is the first order divided difference involving the arguments x1 and x2. Similarly, here f of x2 comma x3, here f of x3 comma x4. These are the first divided differences. The second divided differences are divided delta square f of x, that is f of x1 x2 minus f of x0 x1 all divided by x2 minus x0, which is denoted as f of x0 x1 and x2. Similarly, here f of x1 x2 x3, that is the second order divided difference corresponding to these 3 arguments x1, x2 and x3. Here f of x2, x3 and x4, that is the second order divided difference involving these 3 arguments x2, x3 and x4. Now, the third differences are divided delta cube f of x. Here f of x0, x1, x2 and x3, that is the first order divided difference involving the arguments x0, x1, x2 and x3. For third order, we have to use the 4 arguments. Here f of x1, x2, x3 and x4. The fourth order divided difference is f of x0, x1, x2, x3 and x4. This is the divided difference table corresponding to 5 arguments and the 5 function values. Now, we have an example, that is obtain the divided difference table corresponding to the given data. The given data is values of x are 4, 5, 7, 10 and 11. 4, 5, 7, 10 and 11, and the corresponding function values y equal to f of x are 48, 100, 294, 900 and 1210. These are the y values, that is values of functions at the given arguments. The first order divided difference is divided delta f of x or divided delta y are 100 minus 48 divided by 5 minus 4. In the divided differences, we have to consider the changes in arguments also. This is equal to, the value is 52. The next divided difference, first order divided difference is 294 minus 100 divided by 7 minus 5, which is equal to 97. Next is 900 minus 294 divided by 10 minus 7. The value is 202. And the last one, 1210 minus 900 divided by 11 minus 10, which is equal to 310. These are the first order divided differences. Now, the second order divided differences, divided delta square f of x or divided delta square y, are 97 minus 52 divided by 7 minus 4. Which is equal to 15. Next is 202 minus 97 divided by 10 minus 5. Here we used the arguments 7, 5, 10, therefore 10 minus 5. The value is 21. And the next second order divided difference is 310 minus 202 divided by 11 minus 7, that is equal to 27. And the third order divided differences, divided delta cube f of x, are 21 minus 15 divided by 10 minus 4, which is equal to 1. Next is 27 minus 21 divided by 11 minus 5, 11 minus 5, which is equal to 1. And the fourth order divided difference, delta raised to divided delta raised to 4 f of x is 1 minus 1 is 0. Now, that is 1 minus 1 divided by 11 minus 4, that is equal to 0. This is the divided difference table corresponding to the given data. Now, we have to discuss some properties of divided differences. First property is the divided differences are symmetrical in all their arguments. That is, the value of any divided difference is independent of the order of the arguments. To prove this, consider the divided difference between the two arguments x 0 and x 1. By definition, this is equal to f of x 1 minus f of x 0 divided by x 1 minus x 0, by definition of first order divided difference, which can be written as f of x naught minus f of x1 divided by x naught minus x1. By definition of divided difference, we can write this as first divided difference between the arguments x1 and x0. Also, from this we can write f of x naught x1 as f of x0 divided by x0 minus x1 minus f of x1 divided by x0 minus 1, which is equal to f of x naught divided by x naught minus x1 plus f of x1 divided by x1 minus x0. Now, the first divided difference between x naught, x1 and x2 is defined as, by definition, f of x1 x2 minus f of x0 x1 divided by x2 minus x naught, by definition of second order divided differences. That is equal to, this is equal to 1 by x2 minus x0 into f of x1 divided by x1 minus x2 plus f of x2 divided by x2 minus x2. We have to write f of x1 x2 like this, that f of x naught x1 is equal to f of x naught by x naught minus x1 plus f of x1 by x1 minus x naught. Similarly, we can write f of x1 x2 as f of x1 divided by x1 minus x2 plus f of x2 divided by x2 minus x1, like this we write f of x1 x2 minus f of x naught x1 is this, f of x naught by x naught minus x1 plus f of x1 divided by x1 minus x0. 1 by x2 minus x0 is common, which is equal to 1 by x2 minus x naught into, here first write minus f of x0 divided by x0 minus x1 minus f of x0 divided by x0 minus x1 plus we take f of x1 in common, then we have to write 1 by x1 minus x2 and the term containing f of x1 is this, that is minus 1 by x1 minus x0 plus the remaining term is f of x2 divided by x2 minus x1. One by x2 minus x0 is common. This is equal to 1 by x2 minus x0 into f of x0 divided by x1 minus x0 plus f of x1 into, here x1 minus x2 into on cross multiplication we get this is x1 minus x0 minus of x1 minus x2, that is x1 and x1 cancelled. The remaining terms are negative x0 plus x2, that is x2 minus x0 divided by x1 minus x2 into x1 minus x0. x1 minus x2 into x1 minus x0 in the denominator plus f of x2 divided by x2 minus x1, that is equal to f of x0 divided by x2 minus x0. We just open this bracket, that is equal to f of x0 divided by x2 minus x0 into x1 minus x0 plus f of x1 divided by here x2 minus x0 and x2 minus x0 cancelled, in the denominator x1 minus x2 into x1 minus x0 plus f of x2 divided by x2 minus x0 into x2 minus x1. That is, this is equal to f of x0 divided by x0 minus x1 into x0 minus x2 plus f of x1 divided by x1 minus f of x1 divided by x1 minus x0 into x1 minus x2 plus f of x2 divided by x2 minus x0 into x2 minus x1. That is, we have to observe that this f of this is f of x0, x1, x2, that is the second order divided difference corresponding to arguments x0, x1 and x2 is not unaltered when any two of the arguments are interchanged and hence symmetric in the arguments. Proceeding like this, in this manner, we can show that f of x0, x1, x2, etc., xn, that is the divided differences between the arguments x0, x1 up to xn as symmetrical with respect to any two arguments. Hence, the divided differences of all orders are symmetrical in their arguments. Next property is the linearity property of divided differences. That is, the divided difference operator divided delta is linear. That is, divided delta of a into f of x plus b into g of x is equal to a into divided delta f of x plus b into divided delta g of x. By definition, the divided difference, divided del, x1 of a f of x naught plus b into g of x naught is equal to a into f of x1 plus b into g of x1 minus a into f of x naught plus b into g of x naught all divided by x1 minus x0. This is from the definition of first order divider difference of the arguments x0 and x1. This is equal to, the right hand side is a into f of x1 minus f of x0, a is common, divided by x1 minus x0 plus b into g of x1 minus b into g of x0. B can be taken common, divided by x1 minus x0. This is equal to a into, by definition of first order divider difference, this is divider difference corresponding to arguments x0 and x1, plus this is b into, by definition of first order divider difference, this is divider difference between the arguments x1 and x0 and x1. Here g function is g of x, that is the divided difference operator divided delta is linear. In general, we can prove divided delta a into f of x plus b into g of x is equal to a into divided delta f of x plus b into divided delta g of x. We just proved for two arguments x0 and x1. If we proceed like this, we have to prove in general as the divided delta is linear, the operator divided delta is linear. The property, this linearity property is true with respect to all the higher order differences also. Now, let me conclude this session. In this session, we discussed the new difference, namely divider difference, and we explained the difference table and some properties of divider difference operator divider delta. Thank you for watching this session. Have a nice day.